对啊，白平衡为什么变这样？不知道这样子大家还看得清楚吗？Hello. Okay, let me set up the streaming first. OK. 同学大家看得清楚吗？这个白平衡怪怪的。里面瞧瞧。OK， 在现场可能会，我投影机稍微有点问题。OK， so yeah, let's get started. So as you probably all know, the school's COVID policy has changed, and yeah, starting from tomorrow, every class will be pushed to online. And yeah, this is a little faster than this year. This year was like next week. Anyway, yeah, we will be online, and unfortunately, that means our midterm will also be online. And so I did a little adjustment to the midterm. So first, we will have some kind of online, what's it called? 有点线上监考 okay. And yeah, so obviously we cannot do too much, but we're asking you to connect to this Google Meet in the testing time. And yeah, this is the open preview, and you should turn on your camera to make sure you are actually there, writing the exam by yourself. And how the questions are given out is it will be posted like a homework on eLearn at 3:30. So yeah, 3:30 like the usual time, and you should upload your answer to eLearn. And yeah, so you need to find some way to scan or take a picture of your exam. Make sure everything is really readable. Yeah, we are going to grade on the electronic file. And so find some way to upload your answer to eLearn before 6. So you got given some extra time because yeah, I give you extra 30 minutes to find a way to upload your answer. And there will also be yeah, there will also be a testing file that just let you to try to upload on eLearn to see if there are any technical problems. I think the testing file is already on eLearn. Okay, so if you haven't tried uploading on eLearn, you can try uploading there. Okay, and about open or closed book, I think I will try to keep this one page of notes restriction, although it's kind of hard to enforce, so it's kind of honor system. But those two things I hope that no one really do. So obviously don't discuss with other people, and don't ask your classmates, don't ask people online, don't ask other people. Do the exam by yourself, and don't look up solutions. Yeah, even though you might find some material. And yeah, so obviously this is the only kind of monitoring we'll have, so there might be some flaws, but we still reserve the right to fail you if you get caught somehow, or you are getting posted online, and that's really bad. So yeah, don't do bad things, so we don't need to deal with that. 平板写上传应该可以吧？就是反正你写好能够上传，然后我们看懂就可以了。然后当然也是记得要写名字之类的。对，我不过上传然后自动会有名字，所以可能这一点都是好一点。对 ，OK。So yeah, any question about the online testing rules? Be okay, and yeah. yeah, the quadrant might be changing more because it's online. So if there is no quadrant about the formatting, yeah. So anyway, so the usual class will also be online, and I think the general idea now is we'll do it on YouTube, but we're not very sure. We will do more testing, and we'll make an announcement about how we'll proceed with our class. Although, yeah, there are recording from this year, so you can kind of already check all the videos. It's on the website. Yeah, and I guess, yeah, hopefully we can return to normal after 2 weeks, but we don't know. Yeah. Any question about the course going online? If not, then let's go to the review part that you might be a little more interested in. Okay, review part. So this is like, we have like a 2-page of everything you need to know about chapter 3, chapter 4. Okay. So this is the most important page. One of the most important page in chapter 3, that is, we have this idea that these two functions, so the exponentials, e to the st for some constant s, or in terms of discrete time, so the same thing, but e to the s we can write zn instead, or z to n, those two functions, so those exponential functions, we prove that they are eigenfunctions of continuous time discrete time LTI system. Okay, and this is really interesting. I always think it is kind of surprising because those functions are fixed functions, but they are eigenfunctions for any LTI system. Okay, so any LTI system, they have same set of eigenfunctions. Okay, and this is why we can analyze them really efficiently. And so the only thing marking a difference of the LTI system are that they have the same eigenfunction, but they have different eigenvalues. So in terms of continuous time system, we call the eigenvalues h of s. So it means that you fix on s, and you put in LTI system, you will output also e to st, but it will get multiplied by some constant that depend on this s here. Okay, so we call that h of s. And in terms of discrete time, the eigenvalue will be this big H of z. And then we skip lots of derivation, but later on we learn that this big H and the small h we talk about in chapter 2 has a really nice connection. So this big H is actually a Fourier transform of small h in continuous time. And also this is kind of in chapter 5, but for completeness we also put it here. So it's big H of e to the j omega, means that when putting z equal to j omega, is also a Fourier transform of the small h of discrete time. Okay. So yeah, so the system function, which are the eigenvalues of those eigenfunctions, are Fourier transform of the small h, the impulse response we talked about in chapter 2. So we see that small h and the big H are two different ways to characterize your LTI system. They both tell you everything about your LTI system. And you can see that from those two equations down here once again. So in chapter 2, we talk about you have a LTI system and you got a small h. Then you can compute your output y of t as a convolution between h of t and x of t. And later on, I think in chapter 4, we talk about because of the convolution multiplication duality property of Fourier transform, you can Fourier transform everything in the frequency domain, and you get a nicer equation where you see the big Y is big H times big X. Okay? And yeah, so it's really easy to calculate big Y if you go to everything, put everything in frequency domain. So one way to get Y is you transform your H and X to big H and big X, and just do multiplication here, then Fourier transform back, you can get your small y. And this is also true for discrete time. So discrete time, your output y is this discrete convolution between small h and small x, and you go to frequency domain, you have big Y equal to multiplication of big H and big X. Okay, and so any question about this page? It told you this is the most important part about how you use Fourier transform to characterize LTI system. Okay, and also now we want to talk about what are the Fourier transforms. So we have this nice picture actually from chapter 5. So this part is actually not in our test. Once again, it's not in our tensor range because in chapter 5. But it's nice to put everything in a table. So we have 4 kinds of Fourier transforms or Fourier series. Okay. So in chapter 3, we'll talk about if we have periodic signals. And we have periodic signals, then we can write them as combination of these complex exponentials and you have coefficients ak, and you can transform back and forth between xt and ak using, if it's continuous time, you use this, and if it's discrete time, then xn and ak you can transform back and forth using this equation. And then chapter 4, we talk about a periodic signal, and those are Fourier transform inside a Fourier series, because you can get big X here instead of AK. Okay? So big X is the continuous function, AK is some discrete value. And transform back and forth use this equation. And in chapter 5, you use different equation. Okay? Chapter 5 is about this being discrete. But the test area are those 3 things. Okay? So really, if you can just know those 2 slides, and you can kind of answer every question. You should be able to derive every answer you want in a test. But obviously there are a little more. Okay, so first let's give some high resolution formulas for those 3, because those equations are kind of small here. Okay, so once again, so those 3 blocks, right? 3 blocks here, and so the first one is periodic and continuous. So Fourier series means the signal is periodic. So periodic continuous time, then you have Fourier series. Then what you want to do is you want to write your XOT as some different complex exponentials, and you can find this AK using this multiplying with the negative of complex exponential and integrating over a period. Okay, and details that you can look over. And then discrete time. Now we have this very symmetric formula. So once again, you want to write your discrete S of n as complex exponentials. But now an is also going to be periodic. Because xn is discrete, we have this kind of duality. We talk about that, where xn is dual, is xn is discrete, and a will be kind of periodic with period 2 pi. Actually, well, here we are in terms of k. So k is periodic with period big N. But if you have omega naught times k, then it's periodic in 2 pi. Okay. And so it's very similar, but the difference, kind of what we are going to talk about next, is that so the difference between those 2, one of the big differences is this thing is always convergent, because everything, you are only signing over finite terms. Okay, so this is quite nice. There is no convergence issue. But for the series of discrete time, for discrete Fourier transform back and forth formula is this thing. Okay, and now we have this notation of bracket that means that you are signing over some continuous I guess some consecutive number n big N numbers. Okay, and then we have this Fourier transform back and forth formula. Now the normalization, I guess the normalization is a little similar. Then anyway, we have I should put now the normalization is a little different. I should probably switch those two. Okay, so this x of t is big X and the integral over e to the j omega t once again. But now those are like the first equation, and so somehow we now have the 1/2 pi normalization factor on the first equation, and then the inverse relation we have the big X once again is small x times to this e to the minus j omega t. You can see it's like this minus e to the jk. Okay. Although the normalization we choose to put 2 pi on this big small x equation. So those are equations, and once again I summarize here. So any question on the equations? No? Okay, then maybe we'll stop very early today. And then now we have the convergence on Fourier series. So so this slide is for is for the Fourier series, so the discrete time case. So once again, it's for this one, but it's very similar for the Fourier transform too. And remember, there is no convergence issue for the discrete time periodic case. Okay. Generally, discrete time you have much less convergence issue. But anyway, so if you want your Fourier series to convergent, there are basically two possibilities. One is you have finite energy, and we show that if your signal has finite energy over one period, then the energy in the area will go to 0. And also the other thing is the Dirichlet conditions. If we satisfy the Dirichlet conditions, then for every t, xn of t will converge. So the series sum will converge to the actual value. And the three conditions are first absolutely integrable. So if you take absolute value and integrate it, it should be finite. So it's very similar to this thing, but you don't have a square here. And also over one period, you should have finite number of maximum and minimum. And over one period, you should have finite number of discontinuity. Okay, so Dirichlet conditions, and even if you satisfy the Dirichlet condition, there can be also weird things. You can still have this Gibbs phenomena where you have a weird ripple that gets compressed, but the height stays the same. Okay, and as we said, you have those similar conditions also for the Fourier transform, but instead of integrating over one period, you're integrating from minus infinity to infinity. So, question? No? Okay. Then, now another property we spent quite a lot of time talking about are the conjugation relationship. And so there are really four things, right? So we derive that if x of t is real, then big X, big X, and when you can conjugate, then you will also, well, you can switch this around a little bit, quite a bit. But basically, big X will go equal to big X conjugate and negative negation omega. And this relation, and if it is imaginary, then you get an extra negative sign here. And this is written in terms of Fourier transform, but this is really true for all four things. So once again, these all four things, and you all have a similar relation. Where if x of t is real, then this ak will go ak will equal to ak conjugate minus k, and xj omega will equal to x conjugate minus j minus omega, and etc. Okay, and okay, so that's the real and the imaginary. And also, if x of t is even, then big X is also going to even. And the x t is odd, then big X is going to be odd. And this is also true for AK. So if x of t is even, then ak is going to be equal to a minus k. Okay. And then you can combine those 4 into other 4. Okay. And I think the most interesting are if it's real and even, then big A is equal to real and even, and also if it's imaginary and even, and it's also imaginary and even. And we can kind of break it into those, right? So you can break x equal to even part plus odd part, and then you break the even part into a real and even part, and imaginary and even part, and odd part into a real and odd part, and imaginary and odd part. And because of this even, odd thing, so you know, big X also break into the even part and odd part, and you know the even part are the Fourier transform on each other, and odd part of the Fourier transform on each other. Okay. Now you break the even part into real and imaginary, then you look here, then the real even should also go to real and even, and imaginary and even should also go to imaginary and even. And the other part is the flip around. So you have a real and odd, that should be go to the imaginary and odd, and imaginary and odd, you should correspond to the real and the odd. Okay. So any question? And yeah, in particular, okay, it's a little weird. I think it's okay. But in particular, so x of t is real, then we talk a little bit about this. So if x of t is real, then the even part of xt will, so to look at the real part, so if t is real, then even part of xt will be correspond to the real part of, so even part of xt correspond to the real part of big X, and the odd part of xt will correspond to the imaginary part of big X. Okay. So that's a special case. And so question on the conjugation. And then we have those properties, and I guess we don't. So those tables will be provided for the exam. And also the 5.3 should be provided for. So the very beginning of the Fourier transform formula should be provided for the exam. Okay. And yeah, so this is really a summary, and they are always similar. So I guess let's look at this one. It's bigger. Okay. So obviously we have linearity, and we have time shifting. Then we'll get the HR complex exponential, and the frequency also get the extra complex exponential with plus sign, and conjugation, as we said. Oh no, there is no symmetry here. It's just whenever you do conjugation, then you get the conjugation and the negation of frequency. And then there is a time reversal, which is a special case of this time and frequency scaling. So this time frequency scaling is something interesting. So you get stretch out in the time domain, you get compressing the frequency domain, and also with this 1/a factor. And this convolution and the multiplication property we kind of already talked about. So you have a convolution on time domain will transform to a multiplication on frequency domain, and vice versa. And then you can do differentiation, you get the h j omega, and you do integration, you get 1/j omega, but also this weird delta function term. Okay, you just need to remember pi x of 0 delta. And also if you do differentiation in the frequency, then you get the minus jt here. So you can move the minus j to here, plus j here. And the conjugation property we'll talk about. So if x of the real, then you can know lots of things. So if x is the real, then you know the real part is even, and the imaginary part is odd, and also the magnitude is even, and the angle is odd. And the other things we talk about. Okay. And also this possible relationship, which is true for all sorts of Fourier transform. So, but there are these different normalization vector you need to remember. And so for this continuous time, then we have the total energy from minus infinity to infinity in time domain equals also total energy from minus infinity to infinity in the frequency domain, but divided by 2 pi. Okay? And you can also write this in general form as an inner product. And let's check the different possible relationship have different normalization, because the Fourier transform formula also have kind of different normalization. You can see it's 1 over n here and 1 over t here. And you can also see the conjugations all have a similar equation. Okay? And but for the differentiation and integration, they are all a little weird, and you need to be careful about the difference. So the integration here, you need one integration to be finite, and you need a constant to be 0, etc. Okay. Any question about the properties? Okay. Yeah, weird periodic convolution. And then there is this idea about filters, which we'll talk a lot about. Hopefully you are already familiar with this. So filters are those functions that, or like, as you say, filters are a LTI system that when you write their system function, so the response in a frequency domain, it looks like a square wave. So it's 1 somewhere and 0 other place. And for the place that 1 is called a passband, and when 0 is called stopband. So idea of these filters, you will filter out frequency response in some range. Okay. And now there are high pass filter and a low pass filter. So this is a low pass filter because you will filter out the low frequency things, and you can have high pass filter, you will filter out high frequency thing, or band pass filter out between some frequency. And if it's periodic, then frequency domain everything is periodic. Sorry, if you are discrete time, if your signal is discrete time, then everything in frequency domain will be periodic with period 2 pi. This is kind of in chapter 5, but we also talk about this in chapter 3. So, but anyway, so everything is periodic with period 2 pi. And so low pass filter means you filter out things around 0. And that also means you filter out around 2 pi, minus 2 pi, etc. And high pass filter means you filter out around plus minus pi, or plus minus 3 pi, and then you can have a band pass filter. Okay, so those are filters. It's just some concept, and obviously when you do the Fourier transform, we'll have those later. When you do the Fourier transform, it's the Fourier transform of the Sugar function, and it will become sinc over some sine over sine thing. Okay, and yeah, then so it's kind of go back to the first slide. Very useful application of the Fourier transform is you can use them to solve our linear constant coefficient differential equation. So linear constant coefficient differential equation look like this, and so we provide. Okay, never mind. So in chapter 3 we have like ad hoc way to solve this by choosing x of t being eigenfunction. Then chapter 4 we have a more systematic way. That is, you can just Fourier transform this equation, and you see all those differentials becomes j omega, and just move things around because you know big Y should go equal to big H times big X. So you can solve your big H by moving things around, and you see that you can just read the big H directly from this equation. It's some bk j omega to the k over some ak j omega to the k. Okay. and from big H. So you can read your big H from the equation. I guess I should put more slide, but you can read your big H from the equation, and so that kind of already solve your TI system. Then if you want to find like you put some input, what's the output, you can once again use this. Then you multiply big H with big X, you find big Y. Then you do in inverse Fourier transform of your big Y. And sometimes the inverse Fourier transform you think is too annoying, and then you will do this partial fraction expansion. Okay? So if your big X is also in this rational function of j omega, then your big Y is going to be this rational function of j omega. Then the inverse Fourier transform you can actually do without doing any integration by doing this partial fraction expansion, because if it is rational formula, then you can just break them into those partial fractions with some constant ABC, and it will be like a plus j omega, b plus j omega, c plus j omega. Okay, where this ABC are the ABC on the downstairs. Okay, so we think x as the j omega, then you break those as a plus j omega, b plus j omega, and c plus j omega. And there are ways to solve ABC, but this way is just, or down-based way is just you cross multiply everything and compare to the polynomial here, and yeah, you can solve it. And if the degree here is higher, then you get the extra term before. Okay. So that's 2 slides about how you solve differential equation. And let's go a little more here. And a little more things about solving a differential equation. So we talk about if you partial fraction expansion back into a plus j omega, but sometimes you have a plus j omega square or third, then you cannot actually break this into like a plus j omega, and you need to use this formula, those two formula, to do your inverse Fourier transform. And the derivation of this is you do differentiation on this side. And if you want to remember that, then you can check the course slide. Okay. And also the other thing that squeezing here is the Fourier transform of a periodic signal. Okay. And yeah, so with a periodic signal, you can write it in Fourier series like this. But we can also think about the Fourier transform of that. So we can write everything as a Fourier transform. And how we do that is we use this correspondence of, okay, is it too small? Maybe I can zoom in. Okay, so we use this correspondence that we derive that the Fourier transform of e to the j omega t is delta function 2 pi delta omega minus omega. Okay, then with linearity, so if I have a periodic signal, we can write it in its Fourier series, and the Fourier transform is those whole bunch of delta functions. 2 pi summation ak, then delta omega minus k omega naught. So each ak will have a spike at k omega naught. Okay. So we can write, so now we have a periodic function, we also have a Fourier transform as a whole bunch of delta function. Okay. And then once again, this table should also be provided on the end of the exam. Okay. And yeah, so a whole bunch of useful things. So this page is basically periodic functions, and it's all generalized, like special case of this thing, right? But so it's kind of a table for Fourier series. So yeah, and so we know cosine can be written as e to the theta plus e to the minus theta, and sine you can break into difference of two complex exponential, and 1 is just omega naught equal to 1. And then we have this periodic square wave can get then we have a periodic square wave can break into this kind of sinc function. Okay. This is sine k over k. Okay. This is more in chapter 5, but you also derive this we also calculate this in chapter 3. So might or might not be your exam. And yeah, so those sinc functions are really fun. So we play those. Oh, why is this? Okay, I should edit this sometime later. Yeah, so we also have this square wave function and sinc function correspondence. So it's quite interesting. If you have a square wave function in time domain, we'll get a sinc function in the frequency domain, where sinc function is just sine x over x. And then you have, well, also with normalization. I think this is the actual sinc function. So sine omega t. I think the actual normalization is you have a pi down here. But anyway, then you have a sinc function in the time domain, then you have square wave in the frequency domain. Okay. And also another interesting one is this impulse train. I'm not sure we'll get to talk about how they are useful, but yeah, you have an impulse train in a time domain, and you get another impulse train in a frequency domain. And where the spacing is higher here, so spacing is big T, and spacing will be smaller here. Okay. It's nice symmetry and something you probably want to remember even after the class, because yeah, it can be useful. And then finally, you have delta function transform to 1, and then you use the integration formula. Then you have unit state function transform to this 1 over j omega plus weird delta function. Okay. And I think that's it. Any question? Otherwise, we'll stop early. No? Okay. Then good luck on the midterm. Any question online? Okay, then let's stop.